Hi, I want to go over this problem that we talked about in class, but try to summarize it relatively quickly here. So here is the beam in equilibrium. So what we have is a meter stick, something about a meter long right there. And what we have here is a mass, let's just call it 1 kilogram. And let's also say that gravity is approximately equal to, the acceleration due to gravity is 10 meters per second squared. And the mass is 1 kilogram. So the question is, what is F1, the force provided by this postal scale that's pushing up on this part of the beam, and what is F2, the force pushing up here? All right? So we're going to try to solve this. We want to know F1 and F2. We're going to try to write two equations and then use them to figure out what F1 and F2 must be. So if I do a force diagram on this thing, it roughly looks something like this. I've got mg pointing down, I've got F2 pointing up, and I've got F1 pointing up, something like this. If this thing is in static equilibrium, then the sum of the forces in the y direction must equal 0. And so what that allows me to do is basically say mg is pointing down, F1 is pointing up, and F2 is pointing up. These things have to equal 0. So this is a valid equation. Everything's good with that. How do you make further progress on it? Because this is just one equation. I've got two variables, F1 and F2. The way you make further progress on it is by resorting to a sum of the torque type of equation like this. And if I draw this thing again, it looks roughly like this. mg here, and F1 there, and F2 there. Now, I can go into this, and if I want to do the torques, I could do the torques around this point, or this point, or this point, or even something like this point. But a pro tip is to pick some sort of pivot point around which you're going to sum the torques that will allow you to eliminate one of the forces. So just for variety, let me just pick this one right here, okay? So we're going to pick that point right there where the mass is and try to sum torques around that point. So let's go to it. And what we have is something that looks like this. Actually, I'm going to do this one here. Let me write this guy. F1 is going in that direction, and the distance of F1 to the pivot point is 4L divided by 5. So that's the pivot point there. So I've got one torque like that. I've got another torque that's acting in this direction. I've got F2 like this, and this distance is L divided by 5. So we put the mass 1/5 away from the postal scale on the right end. So we got these two torques. The first torque with F1 is operating in the clockwise direction. So that means in physics, it's going to be a negative torque. So I've got something like this. Sum of the torques equals 0. That means minus 4L over 5 times F1. That's going in the negative direction. And then this second torque is going in the positive direction. It's going to cause things to rotate in the counterclockwise direction. So I can say plus L over 5 times F2, and that whole thing equals 0. So moving one of the parts to one side, I should get something like this. I should get L over 5 times F2 equals 4 over 5 times L times F1. I can cancel the L's, I can cancel the 5's, and I can say then that F2 equals 4 times F1. So F1 is smaller. It has to be added up or multiplied 4 times to equal F2. So this is my next equation. This is going to allow me to substitute into this equation up here. So I'm going to copy this equation down below. This is our sum of the forces in y, minus mg plus F1 plus F2 equals 0. Minus mg plus F1 plus F2 equals 0. And I can sub in for F2, minus mg plus F1 plus, so F2 is 4F1 equals 0. So now I've got 5F1 equals mg. So these guys combine to give 5. And then I can take mg divided by 5 and say that that's equal to force 1. Now, force 1 is solved for with that, but I also know from up here, this equation here, that 4 times force 1 equals force 2. So force 2 has got to equal 4 times this, which is 4 mg divided by 5. So this then solves for the two forces if we're given m and g. And we actually don't even need to know the length of the stick. It's just as long as we know the proportion of where this mass was placed. If it was only placed 1/5 away from postal scale F2 versus 4/5 away from postal scale F1, then we know that 4/5 of it will be borne by F2, which is the postal scale that's closer to where the mass is. So that's an example of how you can solve the beam and equilibrium problem. I hope that was helpful. Feel free to leave comments below or give me hints about how you want further videos to be done.